Thank you. So this is our first meetup in East Bay, which is awesome because I live in Oakland. So yay, East Bay. Yeah, so how many of you guys live in Berkeley? How about Oakland? How about further west or east, I guess? Okay, cool. We've talked about doing like a San Ramon meetup too, so if that's interesting to you, let us know. Okay, cool. All right, so how many of you have ever either, how about this? How many have heard of H2O before coming here? Okay, and then how many of you have actually tried it out? Okay, so like a handful. Okay, good, because it might be a little bit boring if you already know how to use H2O, but you might learn something new regardless. But this was kind of like meant to teach you a little bit about what it is and why is it different from other machine learning software, and then we'll teach you actually how to use it so that you should be pretty proficient by the end of the hour. Okay. So I work at H2O. So H2O is a company that's in Mountain View, and the whole purpose of H2O is to produce this software. So it was from the very beginning, the whole point of the company was to make a company that would produce open source machine learning software that would work at scale. So I'm from around here. Like I went to Berkeley and did my PhD there in biostat. Graduated a few years ago. But mostly what I worked on there was making machine learning software that would scale, essentially. Somehow they gave me a PhD for that. But yeah, so, and then I've worked at a few startups doing data science, one of which was in Berkeley called Wise.io, which doesn't exist anymore because it was just bought by GE. Okay, so first of all, who and what is H2O is what we're going to talk about. Then I'm going to explain what the actual platform is. And then we're going to talk about how to use it from R and Python, because that's where most of our users, how they use it. And then we'll do some tutorials. And then I'm going to hopefully have enough time to spend a little bit of the hour talking about the new projects that we're working on. And I should also mention, if you don't write code, you can actually also use H2O from our web GUI, and everything that that we teach you how to do from R and Python, you can do through like drop down and clicking around. So even if you do know how to write code, sometimes it's just nice to not have to write code. Okay, so H2O is a company that's been around for a couple of years, and right now we're around like 80 people. And there's some sort of affiliations with Stanford and Purdue, which I'll explain further in a minute. And then H2O is also the name of the software that we produce. We're starting to produce other things that have other water names. So sparkling water, deep water, there's all versions of H2O, which we'll also get into. Anyway, that software is open source. Apache 2.0 if you care about licensing. And again, the whole point is we've rewritten like all these machine learning algorithms from scratch so they can work on distributed systems. And they also work just as well on your laptop if you just want like a kind of like a faster machine learning library to use. And quite honestly, a lot of people use it that way. Okay, and then these are our Stanford people that we're connected with. So if you're sort of familiar with machine learning, you might know this book called The Elements of Statistical Learning. And that's written by the first two guys there, Trevor Hastie and Rob Tibshirani. So if you don't know that book, it's a good book, and it's also free on their website. So, and they actually have another version that's something like Intro to Statistical Learning that's also pretty good. Okay, so I'm going to explain what the H2O platform is. And so I use the term platform instead of machine learning library or some other word that you could use, I guess, because it's inclusive of a library that does machine learning and also sort of a data processing platform that's distributed and uses distributed data frames. And so we had to build sort of the infrastructure to do the distributed algorithms. And so, but you can call it whatever you want, but that's kind of the word that I like to use. All right, so this should be pretty drilled in by now, but basically it's distributed implementations of what we consider to be the best machine learning algorithms. And everything, all the algorithms are written in Java, but we have APIs in R, Python, and Scala, and a web GUI that I mentioned. The name of our web GUI is H2O Flow. And then there's another product called H2O Steam that is, I won't really talk about it, but it's used if you're trying to productionize the models. It's sort of all the DevOps tools around that. You don't really need Steam, but it's kind of this extra tool that we have to help with that process. So the goal with H2O is so that like normal people with like R, or, basic R Python skills can do distributed computing. And then the other thing is we output the models in as a Java code itself. You can also save them like as a binary file like you would do with other machine learning libraries like scikit-learn. But this is kind of like, if you're trying to put these into production, we give you like a sort of one-click way to do that. You just export the model and it will be exported as Java code. And that's why a lot of companies use H2O, is because there used to be sort of, I don't know if it's like this still happens or how often this happens, but sort of the 5 years ago thing that people would do would be they'd hire some data scientists to write, and they would code in R Python, and then they would hand it off to the engineering team, and then they would re-code everything, all the algorithms in Java so they could put it into production. And that's just really inefficient, and it's sort of disempowering to the data scientists as well, because you might even make sophisticated algorithms, and then the engineers might just say, well, too bad, we're going to use a GLM because that's the only thing I really know how to code and can code fast, and so too bad. So that won't happen. And then originally H2O was sort of meant to be the machine, like the good machine learning library for Hadoop when we first started in 2012. Because there was one called Mahout, or Mahout, however you pronounce it, that was kind of like mediocre but never really caught on. So, and then Spark came along, so we sort of rewrote everything so that it would work with Spark as well. And so we're actually in the third incarnation of H2O, and so that's why our GitHub repo is called H2O-3, if you are paying attention to such things. And then you can also just run it on your computer. You don't need Hadoop or Spark. So if this is sort of meant for, like, if you already have that infrastructure and that's sort of what you're locked down to, it will work with that as well. Okay, and so this is kind of my one, like, really technical slide, is just to introduce you to two concepts that we have in H2O related to distributed computing. So one is what we call the H2O cluster, and so that's just the name for the Java process that's running either across your physical cluster, or if you're just running it on your laptop, like a little miniature cluster. And that's where all the, all the magic happens. So that's like all the models are in there, all the data frames are in there, and that's distributed, and it's essentially a really large distributed key value store, if you're familiar with that term. And then the way that you scale that cluster is you just add more nodes to your cluster. And then the H2O frame is the other concept. So this is essentially a data frame. Like if you're used to R, there's R data frames. If Pandas and Python, there's data frames. It's the same thing, except for it's actually distributed. So you don't know that when you're writing the code, and it doesn't really matter to you. But if you actually are running it on a multi-node cluster, the way that it's chopped up is, some subset of the rows is on one machine, some other subset is on another machine, and split up by row. But it functions as like one cohesive H2O frame. And then the way that you do like data munging with these frames is like the same as you would do in R or Python. So we basically implemented all of the methods that you would, I won't say all, that's not true. most of the methods that, that you should be able to do on an R data frame or a Pandas data frame, you can do on an H2O frame in a distributed way. Okay. And here's just a list of some of, well, I guess this is fairly accurate. There's maybe one algorithm missing on here or two. So this is just a list of all the algorithms that we've implemented from scratch, basically. So these are all sort of modern, popular algorithms. There's two that are not on here, actually. So we just released a Word2Vec implementation. So that's for text processing. That's not really listed on here. And then we have some new stuff that's, I don't think it's like officially released, but it's on our GitHub, which is these model interpretability algorithms. So you essentially have a tool that can tell you why the predictions were made and how they were made. Because that's like, you know, just a recurring theme for all of our customers and all of the people that we deal with is like, we want to use this model, but we don't understand why it's making the predictions, and maybe they're in like a regulated industry, so they have to understand. So we're building up a lot of tools around model interpretability. Okay, so now let's talk about using it in R and Python. So in R and in Python, it's just a package. So for R, you would download from CRAN, so just install packages H2O. And then for Python, same idea, like pip install H2O. And so then that will, you know, give you the whole thing. You don't have to install any like distributed libraries or Java or anything like that. It's just all self-contained. So sometimes when you use distributed machine learning algorithms, you have to actually install like other software on your computer to enable that. So this is, we've done all of the, we've created all the software itself, so we don't actually depend on any other libraries to do the distributed computing stuff. What's that? Content. Oh, yes. Yeah, you can. And so the idea with both or all of our APIs really is that you're writing code in either R, Python, or whatnot, and then nothing's actually happening in R or Python. It's just sort of translating that into actually a long REST call that gets sent to the H2O cluster, and everything then happens there. So you're just sort of giving it instructions of what it should do, like import this data set, train a model, get the results, etc. And so you could actually be running this on a really crappy computer with just a Python shell, and then maybe your cluster is on AWS or something like that. So so yeah, you don't need a lot of memory to drive this thing. You just need a nice, if you have big data, then you would need like a big cluster to use this. So any questions on that? So how many of you, I don't like to partition people into languages, but I'm going to. So how many of you are like consider yourselves more of an R person if you have to choose? Oh no, only 2. Okay, 3. Okay. How about Python? Oh wow, that's overwhelming amount of Python people. Okay, so when we're going through the scripts, we'll do the Python version, I guess. Unless I wanted to be a jerk, then I would do the R, but I won't do that. Okay, so if you want to, so next we're going to just kind of go over just some basic code and how do you import data, how do you train a model with the libraries. So if you want to follow along, you can on your computer, and so that's the location of the code that we're going to go through. So yeah. You're running everything on your laptops. So that's actually one of the questions that people have is like, is there like an H2O cloud, like sort of like, what's the scam? Like where, it's like fully open source software, and it's like you're running it on your laptop or your cluster or wherever you want. Or you could run it on Amazon EC2 or any of the other cloud things. But there's not a thing that's like an H2O cloud where we make you like do it there and pay us money. So although people have asked us to do that, so maybe in the future. Yeah, so H2O tutorials. So our GitHub is H2O AI as our user, and then this is where we put a lot of our tutorial data, or not data, but scripts. Okay, so this is that repo. So let me just show you the H2O GitHub. All right, so there's H2O3. That's like the main H2O code base. Then there's, you know, we actually have more repositories on here than you can see, but the sort of highlighted ones, Sparkling Water is the name of our Spark package that allows you to use H2O on Spark. This is a good one to know. This is our meetups directory. So all of the slides from all of our meetups forever basically are in here. So including the ones that I'm showing you right now. So if you wanted to download these slides, you scroll, it's sort of in order. So there's East Bay Meetup, there's a keynote and a PDF here. So if you want a copy of these slides, that's where to find them. And this also, like, you can kind of look through all of our stuff. And if you're interested in more advanced topics. Okay, so tutorials. Yeah, we do. And some of the new stuff that we're doing is, which I'll talk about at the end, but basically we've started, for a long time we wrote everything ourselves from scratch, and that was our sort of philosophy about it. But then recently we've started to integrate other open source projects. So XGBoost is a really popular machine learning library that we've integrated, and then all of the new GPU deep learning stuff, so TensorFlow, Caffe, MXNet. So those are most easily distributed in a Docker container because you have to have all this stuff installed and everything to use them. So yeah, some people use Docker, and we use that when we're trying to sort of give somebody a nice environment where everything's all installed. We also have AMIs available on Amazon, so if you just want like an H2O AMI with everything all installed, we also have that. But unless you're using some of the more advanced or third-party libraries, it's just really simple to install this as an R package or a Python package. Okay, so what we're going to do is go over this intro to H2O and Python tutorial. So you'll see there's a lot of stuff in here, and that's why I've sort of bookmarked these as the main ones that you want to get introduced to when you're getting started. So, all right. So maybe I'll actually, instead of just showing you the code, maybe I'll run it as well. So if you want to actually run this code, so you have two options. One, you can just git clone or download the whole H2O tutorials repository. Okay. But there's a lot of stuff in there, so there's a lot of PDFs and other stuff. So if you just want the notebook, then you can just how do you do that? I think you just right-click somewhere. I forget, I've done this before. Guys. Nope, not that. Does anyone remember how to do this? So there's, I've forgotten how to download a single file from a repo on GitHub, so I think you can just right-click somewhere here, and is it this? Save link as? Okay, that's how you do it. So if you wanted just this notebook, and you don't want to clone the whole repo, you can download it this way. So you just do a right-click on the raw. All right, so yeah.
You're indicating that everything runs on the laptop. Are there any requirements of the in-memory requirements?
It's all dependent on how big your data set is. So, and actually, we do have some rules of thumb about that. So I think the one that we tell people is like you need at least like 3 times the amount of RAM or memory in your H2O cluster as the size of your data set. So I don't know if that's still the case, but that's what I've heard. But you can always, you know, experiment with that as well and just see. And it'll depend on which algorithm you're running too. So if you're running GLM or something more simple, it probably won't be very much. But if you're running a tree-based algorithm like Random Forest or GBM, it might be a little bit more than that even. Okay, so let me actually go on my desktop and open this up. So what's that? Oh, I'm just using this to open it up, but I can also just show you what I'm doing here. So I'm just going into the tutorials repo. It will open up as a Jupyter notebook, so it'll be easier to see it. So these are some trainings that I made for, we had like what we called the H2O Open Tour like last year, where we had a bunch of conferences and we did some training. So so if you're wondering, if you're kind of following along and you were wondering what I was typing, so I just typed in Jupyter Notebook, Jupyter space notebook. Does everybody know what Jupyter stands for? It stands for Julia, Python, and R. Yeah, that's a little tidbit. For a long time, I didn't realize that Julia was in there. Yeah, that's what it stands for. So, all right, so we've opened up. This is really small. So we're going to do the Intro to H2O IPython notebook. And let me just see if I'm already running H2O and shut it down. Okay. All right. Okay, so I'm going, let me just check the time, 6:55. So I'm going to be talking until 7:30, but I'm going to try to leave a little bit of time at the end to talk about the other projects that we have. Okay, so this assumes that you've already installed the H2O library, so we'll do that. So the first thing you do basically in any scripts when you're using H2O is start up the H2O cluster. So there's an h2o.init function that will do that for you. And most of the time, if you're running it on your laptop, you don't need to set any of the arguments. It'll just start up an H2O cluster on your laptop using all of your cores, essentially. But if you want to control some of the things that are useful to know about our number of threads, you set that to -1, it will essentially use all of, basically a thread per core. So if you have an 8-core laptop, it'll use you know, the most amount of threads, which would be 8. And then max memory size, that's just I think in Python it's just an integer for the gigabytes of RAM. So I think the default is 4 gigs, and that's fine for this demo. But yeah, so sometimes, you know, you have to think about that stuff, but yeah. Either one is fine, and I probably should say that I use Python 2, but you probably should use Python 3 nowadays. Does anyone else have opinions on that? I use both because I have to test for both, but I'm still like a little distrustful of Python 3. All right, so we just import the library, and so what it will do is Oh, the other arguments that I should mention is there's an IP and port argument. So if you're actually running your cluster on Amazon or some other machine, you would put the IP address and port in there. But the default IP is just localhost. So let's see what's happening here. Seems to be running. I also just made edits to the Python API, and I'm working off of a untested branch, so this could be dangerous. I don't know. Let me just stop this. I think it's probably best if I use the proper stable H2O. So let me just pip uninstall H2O. And this will download it from PyPy. So I'm going to go ahead and restart. Okay. Let me try that again. Okay, so now it's working. I must have broke H2O when I was messing around with it. So there's actually a lot of stuff that it prints out, but essentially what it's saying is I'm checking to see if there's already an H2O cluster running at the IP that you've given me, which is localhost, and it said I couldn't find one, so I'm going to start one up for you. So, so it started up an H2O cluster. Let me make this big again. And then it will print out some interesting information about the cluster. So which version are you using? How old is that version? The number of nodes. So I'm on my laptop, so that's one node. Number of cores is 8. So you'll notice that I told it to do 8 gigabytes, but the actual amount of memory that you can use of that is 7.1. So it'll be like a little bit less than what you specify. Yeah, so, and then just because I usually forget to show people the web UI while I'm noticing this right now, I'm just going to bring this up on the side. So this is, you can't see that, but that's where H2O is running. It's running on localhost or 127.0.0.1 and port 54321. So if I go here in a web browser, what you'll see is when we started up the H2O cluster, it actually starts up, one of the many things it does is start up a web server locally and allows you to interact with H2O via the Flow UI. Hold on one moment, please. Okay. Oh, I see what's happening. My computer is backing itself up right now, and it's making everything slow. So I'm going to pause that. Okay. Just try this here. Okay. There's all sorts of weird stuff going on my computer. So just use a different browser. So basically, this is sort of the interface for when you get started, and you can do everything that you need to do, like upload files, you can do modeling, etc. And I'll show you a little bit more of this later, but just an FYI. And if you want to see more of this later, just tell me, like raise your hand. I'll go back to it after we've trained the models and look at them through Flow, because that's typically how I use Flow. Is I'll do everything in R Python, and then I go over to Flow, and you kind of have all these plots that are created automatically for you, and it's sort of just a GUI to like inspect your models. Okay, so we were. Oops, I think I killed my Jupyter notebook. That was bad. Sorry, I'm just going to open this up again. Okay. So, all right, so what we're going to do in this tutorial is essentially show you how to import data into H2O, and then how to train a few models, and then how to evaluate those models. And then I'll point you in the direction of some other tools like grid search and some other things that I think are interesting, like ensemble models of all the models that you train. So what we're going to do here is this is our main. Can you guys see that? Should I make it a little bit bigger? Is that better? One more, or is that good? One more? Okay. Whoa. All right. Okay. So, so the main sort of file importer in H2O is just called h2o.import file. And all of the names of functions in the R and Python API are essentially identical. Sometimes in R we do like import big F, like we do camel case sometimes. So just an FYI. So once you learn one of the APIs, you're practically able to just go over to the other one and do everything that way too. And so import file can import all sorts of different types of files. The easiest thing to deal with, I guess, is CSV. So, or that's probably the most common thing that people are using. So I'll show an example of that, and you can give it a local file, or you can give it a file on the internet. So there's other types of files that we support. We have like sparse SVM-Lite support. You can put an S3 location in there. You can put an HDFS location in there. So essentially wherever your data is, there's probably support for that in this one function. So and while that's, so it actually is downloading the file for me and then importing it into H2O. So so I'll just tell you what this file is. So it's called loan.csv, and it's a file from the Lending Club company. So they do like loans, and the task here is to train a model to predict whether or not people are going to default on their loans. So there's like, I don't know, 13 or 14 features that they collect about the applicants, and then so this is actually historical data, so I guess they're not applicants. They're people who applied for a loan, got a loan, and then they found out whether or not they defaulted. So the response column is binary. It's like yes or no, did they default? But the way that it's encoded in this file is it's a 0 or 1. So the reason I use this example is because this is probably one of the first things that people get confused about with H2O is how to tell it like what task to do if you're doing binary classification or multi-class or regression. All of that is sort of controlled by what is the data type of the response column. So, and in this case, it's actually not listed as true or false or yes or no or something like that. It's a number. So unless you tell H2O that you want it to do binary classification, it's going to think, oh, this is a numeric column type, I should do regression. So, so I'll just point that out as we move forward. And this is just to show the data size. So it's 163,000 columns rows and 15 columns. And again, to sort of emphasize that all of the, methods that you're used to working on like a NumPy array or a Pandas data frame will work here. And if you find one that you want to use and is not implemented, then at the very end, I'll show you how to create a feature request for H2O. And you can just say, hey, there's this thing, why isn't it there? And you can make a feature request. Okay, and so this is the thing that I was just talking about, like how to encode the response variable so that it's properly encoded. So since there's only like 3 R people here, you might not be familiar with the term factor. That comes from R. In Pandas, they just call it categorical. That's probably a more sensible name for it, actually. So we have a method called asFactor, which turns the 0, 1 numeric column into a categorical variable, so a categorical column. And so this is, the standard like Pandas syntax. Data is the name of the data frame. Bad loan is the name of the response column. So that's the 0 or 1. And with categorical columns, data, you have something that are called levels. So these are just the different categories. So in this case, there's just 2, but there could be a number of different categories. And they would just be, this is just asking what are the levels here, and it's spitting it back out. So now we are set up to do a binary classification problem. So one of the first things that people typically do in their data science workflow is they might partition the data into different pieces. So one for training, and then sometimes people just do one for testing, but I always like to do train, validation, and test. And so I think for like, I don't know, 3 years when I heard validation and test, they like mapped to the same thing in my brain, and I didn't know that there was actually a difference. So I'll just explain what that is in case you're me from like 5 years ago. So train is just for training the model. Validation is actually also for training the model, but in a different sense. So you use a validation frame to sort of tune the model. So with H2O, all of our models have something that we call early stopping. So for example, in a GBM, it's easy to, a gradient boosting machine, if you're familiar with that algorithm, you can tell it how many trees to use in the GBM. And so it's easy to sort of overfit if you give it too many trees. So what you can do is you can use a validation set to figure out when to stop adding trees. And so you could say, do 1,000 trees, but actually you can stop anytime before that if the performance doesn't increase. So validation is used for sort of tuning the model itself. And then test is always just used once. So if you're using test set more than once, you're breaking a rule of data science, I guess. So that's always the litmus test for, like, if you've used the test set more than once, you're like cheating or something. So I don't know if that makes sense, but maybe you'll see exactly what I'm talking about as we go forward. And so we just have this split frame method where you tell it like what percentages you want it to split in, and this will actually split it into 3 pieces, despite the fact that there's 2 numbers there. So it will do 70% and then 15% and then whatever's left. In this case, that would be 15%. If you set a seed like I'm doing here, it'll be reproducible. So it will do the same thing every time. But if you don't, it will just be random. Okay, so did all that. Split the frame. And then one thing that I'm going to point out, because it might be surprising to you, that even though the validation and test set are meant to be the same, percentage of the data, so 15%, they're actually different number of rows. And the reason for that is because this is a very scalable method of splitting data, and I won't actually really explain, but it's what we call approximate splitting, and it's scalable, and you can do it on huge data sets, and you won't get the exact 15% number, but you'll get the expectation of that is that it will be 15%. And I believe we also have a method that will do an exact split if you want that, but I actually don't think I've ever used it. Because really, you don't really necessarily care that the numbers are precise anyway. All right. And before we go on to this next part here, I'm just going to skip below and show you the interface for the algorithms, and then you'll understand what X and Y represent. So this is essentially what all of our at least in Python. I mean, we have the same arguments in the R function, but it's just a single function rather than making an object of class H2O generalized linear estimator and then training it. So there's actually 2 steps here in Python versus 1 in R. But this is, maybe I'll scroll up. This is what I'm trying to show you, is that this is sort of the bare minimum of what you need to give the train method is a training frame, which is your data frame that you use for training, and then X and Y. And so right now you might be wondering, like, isn't that redundant? Isn't X like the training data? Because a lot of machine learning software will use X as the actual data frame itself, and then Y as the response column. But the way that we do this in H2O is these X and Y are actually just like column names or column indices. So it just makes it a little bit easier to, rather than creating a bunch of different frames that have like different columns and things like that, you can just change the X, which is the list of your predictor columns. So before we do that, let's go back up and then we'll look at X and Y. So Y is just this bad loan column. So again, you can use indices or column names, and then we'll create X here. So first I'm going to just create X as the list of all of the names of the columns, and I'm going to remove Y, and then I'm also going to remove this column called interest rate, because if we don't, then we will have a situation of what's called data leakage. In this particular data set, the way that it's used is after they evaluated all of their attributes for an applicant, they assign them an interest rate. So this is actually highly correlated with the outcome, and I'm not going to go into too many details, but in this case it makes sense to remove this, but if that's not making sense to you, just don't worry about it. Okay, so I'm going to run this. I'm going to print out what the predictors are. So if you look at these, they're kind of like things that might make sense in predicting whether or not somebody would default on their loan. So things like loan amount, the term, employment length, home ownership, annual income, et cetera, et cetera. So these are the things that we're going to use to predict. Yeah?
How arbitrary is the cutoff? Obviously, some of these things are correlated to default rate, right? But you said that the interest rate assigned is highly correlated. Where's the split there?
The split.
So like data that you would remove.
Oh, you're saying like, yeah. So there's not probably really a number that you would say if it's like more correlated than this amount, then get rid of it, because it's more about thinking about the actual problem itself. And when you're designing this to be a tool that you can use that only takes the these things as input and then predicts something.
So is it because the rate before that was taken out was like a higher order term, basically?
It's because they probably had their own machine learning algorithm that was generating that interest rate. So it's data essentially that you wouldn't have if you were using this as a tool. Yeah, and so it was just included in there for whatever reason. Yeah. It might. Why don't we see? This will be interesting. Does anyone have any guesses about which of these would be like the most predictive? Because we'll find out. Anyone else want to make a guess? Okay. All right. Well, we'll see. The result might surprise you. What's that? Which one is that? Oh, longest credit length. Yeah, that would also be good. All right, so I'm going to skip down to some of the more exciting algorithms. So GLM is like nothing wrong with it. It's a great algorithm, but it doesn't get like really good performance like some of these other ones. It's useful if you need interpretability or something simple, or if you want to get like p-values or things like that. But as a machine learning algorithm, it's like one of the more, I guess, one of the weaker performing algorithms. So I'm going to skip down to, so I actually went through a bunch of the algorithms in here. We're not going to go through all of them. Let's see. Let's do random forest. So All right, so we need to import the random forest estimator. We decided to use extremely long names for our classes. So you only have to type it like once or twice, but so we import that. So remember how I was saying that we had to encode the response column as a particular thing. So this is why, because we have one method that does all the different problem types: regression, multiclass, binary. In scikit-learn, for example, they have two different ones. They'll have random forest regressor, and then they have random forest classifier, and that's how you tell it what to do. So it's just a slightly different approach. All right, so first we're just going to initialize the random forest estimator. This is the step at which you would put in model parameters that you might want to change from the defaults. And if you want it to be reproducible, you could put seed equals 1. And I hardly ever set model ID. That's just like a name for the model. It makes it easier to find it later if you're working in Flow. But I practically never use it. It'll just create a default one for you. So that basically does nothing. It doesn't do any training. It just sets up the object. And then when we actually want to train, we just do the .train method and then give it the data that we want to train on. Okay. So this is, as all of our algorithms, they have progress bars, which some people love, and it turns out some people hate progress bars. So if you want to turn them off, there's an H2O, I think, like no progress, I think it's called. I don't know. That's what it's called in R. I can't remember. But, you can't win, really. I think they're great, but okay. So we've trained one random forest with all the default model parameters, and we're going to set that aside, and now we're going to train another one, and then the goal will be here to compare the performance between the two. So, so the only thing we're going to change here is the number of trees. So by default, the random forest will train 50 trees. So let's try doubling that number, and unlike GBM, if you keep adding trees to a random forest, it doesn't really overfit. So it's just, after a certain point, you're just wasting your time, but you're not going to probably get yourself into a bad place in terms of model performance. So now we're training twice as many trees. Okay, that's done. Okay, so now we have two models, RFFit1 and RFFit2, and I'm just going to try and see how they do on the test set. And the way that you do that is there's a model performance method. So the two methods that you would want to use at this point, one is model performance, and that's probably good enough. But if you actually want to make the predictions and have the predictions in a data frame, there's a predict method as well. But what model performance will do is it'll make the predictions and then calculate a whole bunch of metrics, and then you can ask it for any of the metrics that we have. So we'll do that. So now we have these performance objects, and from there you can grab out particular metrics that you're interested in. So AUC is typically one that I use if I have a binary classification problem. There's other ones that you can use, but this is one that I like. So so we'll look at the AUC for each of those, and we'll see there's a slight difference. So the one with 100 trees is a little bit better. So for those of you who are not familiar with AUC, it's a metric that essentially goes from 0.5 to 1. And 0.5 means that your algorithm is as good as flipping a coin. It's completely useless. And 1 means it knows everything all the time, 100% correct. So, I like it because it's has the same scale. It's not dependent on your data that you're predicting. It's just, I don't know, and I've used it forever, so maybe that's why I like it. But so yeah, you can see that the second one does a little bit better in terms of test set performance. So then the other thing that you probably want to do is sometimes people like to do cross-validation. Instead of doing a test set or a validation set, they'll just do cross-validation. And if you're not sure what that is, it's basically just, so k-fold cross-validation, if k is 5, then you train 5 models and test 5 models and then average the results together. So you basically divide up your data into 5 chunks. And on the first iteration, you train on these 4 chunks and then test on that one, and then you swap out which one is the test set and then average the results together. So that's another way for you to just see how your model is doing. It's a little bit more robust than just testing it once on a test set, but it takes 5 times as long. So it's sort of a trade-off. And the way that you do this is just one single argument in H2O. So there's, you know, you could write a big loop. I've seen people do all sorts of things and like splitting the data and all that stuff, but we've done that all for you, so you only just have to type in the number of folds that you want. And so if we train this, it's going to take a little bit longer because it's doing basically 6 times the work, so 5 cross-validation folds, and then it trains a final model on the whole data set. So you're actually training 6 models. So we'll wait for that. And then I don't have a whole lot of time left, so maybe I'll just sort of point out the next thing and then just show you one more thing from here. So if you're doing cross-validation, the way that we did the performance before was like we were testing it on like a new data set that the model doesn't know about, so we had to use the model performance method. But if you're doing cross-validation, or if you pass a validation frame, or if you want to know the training metrics, like the training AUC, which you typically don't, but there might be some reason that you would do that, then you can just do the name of the model .AUC and grab it right out of there, because you don't need a new data frame or anything that doesn't know about. So there's 2 ways to get the performance. So cross-val equals true would be one option, train equals 2 will give you the training AUC, and valid equals true will give you validation AUC if you happen to pass a validation frame along. Okay. And then I'm just going to point out one thing with the GVM that I think is pretty useful. So this is something that people typically have to do by hand. So when you're tuning a model, deciding like when to stop training, there's a sort of a trick that people use where they plot the training error and then they plot the validation error. And when they, you know, basically, let's see, training error, they start to go kind of like this, and then what will happen is once they diverge, if you're like plotting like number of trees and error, they start to diverge, and that's like this point at which you're supposed to stop training. Because what happens is if you train too much, then the training error will go down, but then the validation error will start to go up, and then that's not good. It means you've overfit your model. So rather than like trying to manually do this and visually inspect these plots and like look at all of this stuff, we have a way to do this automatically. And this is what I called early stopping before. And I'm just going to explain quickly what how to do this in the GVM, because that's where it's probably the most useful. So if I say number of trees equals 500, and I invoke some of these early stopping arguments, it will stop somewhere before 500 when it's sort of optimally tuned. And so the first one is score tree interval just means how often are you scoring your model on the validation set. That just means every 5 trees, like check where you're at. And then stopping rounds is, well, let me start with stopping metric is the thing that I care about. So I'm interested in AUC, so I'm just telling it which metric to look at. And then stopping tolerance means like when the AUC, in this case, bigger AUC is good. With error, like smaller error is better. But essentially what the combination of all these parameters together means is like the stopping rounds means for 3 consecutive scoring sessions, if the AUC does not increase more than this amount, and that would be the validation AUC, increase more than this amount, then like cut off the training. So this is kind of an advanced feature, but if you if you learn how to use it, it actually makes you more powerful than not using it. So just pointing that out. And let's see. And then I'm just going to do one thing, which is 727. I'll just mention the grid search notebook because it's really, really useful to have a function that does all the grid search for you. And I'll just show you a quick example without running it. This is the same exact data set, so the first bit is the same. So this is how you would train a GBM grid. And is everybody familiar with what a grid search is? Essentially, you give it a list of, these are all parameters that have to do with GBM, so learning rate, max depth, these are called hyperparameters. And these are like the knobs on a machine learning algorithm that you twiddle around until you get like a good model. And this is sort of like the artistic part of, it's not really artistic, but like this is the part that takes a long time to learn, as to how to like give it good ranges of parameters and like all this stuff. And then the grid is essentially the combination of all of these values that you give it. So in this case, we have 2 values for learning rate, 3 values for max depth, et cetera, et cetera. And so it's like the cross product of all of those combinations. So every version of that is represented in the grid. And so that could be a lot of models. So that would be 2 times 3 times 2 times 3, whatever that number is. I should probably know by now. I've like gone over this a number of times. So that's the grid, and to do grid search, there's something called H2O grid search. You just give it in the case of Python, a dictionary, and tell it which model you want to do, and it will go and often do that grid for you. And then if you don't want to wait for like a million models to finish, you can do something called random grid search, where it will randomly sample from that space, and then you can tell it, I want you to do random grid search for an hour and then stop. So these are like what I consider to be really practical like tools for doing data science. Because you used to have to write like so much code to do this stuff. All right, so I'm gonna just go back to my slides for like a couple minutes. This just describes some of the tutorials that we went over. Grid search. This is a screenshot of like if you run the grid search in R, what it will look like. It prints out the different hyperparameters that you looked over. There's 72 models in your grid, and then it will print out like the performance. So this would be like a 72 row data set, and then it tells you each of the things. And then I'm interested in AUC, so it will rank it by AUC, and yeah, so it's just all very self-contained. If you're interested in deep learning, you guys are Python people, but maybe if somebody has a day where they want to spend learning H2O, they could convert this wonderful R tutorial on deep learning into Python, and then we can have a Python version. I'll get around to it eventually, but if somebody else wants to do it, I'm happy to accept your contributions. And then this is one of my favorites, the stacked ensembles, because this is the area of my PhD research. And the idea here is like, especially if you don't know a lot about all the different models, like maybe you just don't even care and you just like train a whole bunch of different models and then, put them together in what's called a stacked ensemble. And so what this does is it actually uses machine learning to learn what the best combination of the models is. So it's not like averaging them together or like coming up with like a weighted sum or something like that. It's actually a sophisticated ensemble where you just give it a bunch of models and it goes and like creates an awesome model out of that. And this is literally like the only way to win Kaggle these days. If you know Kaggle.com, the data science website, this is all that people are doing. So if you want to try Kaggle, this is a good tool. There's a stacked ensemble method. And I'll show you, these are some resources, so you can download the slides and have links to all this stuff, but just because I have your attention, I'll show you the the docs page. And the H2O user guide is like the main thing. And I actually think we haven't changed this yet, but I've asked them to change the documentation to point this out, because there's a lot of links on this page, and I don't know, people get lost. So this is actually, this random link here called H2O user guide is like our main documentation. And this has also been redone and will be out in the next release, because it's kind of getting to be too much stuff on the side. But if you go to data science algorithms, at the bottom, stacked ensembles, that's where it's at. So here's like, if you want to know how to do this in Python, here's an example. All right, I'm a little bit over my time, but oh, I brought some of these booklets. They're also available as PDFs on that same page that I just showed you, but we have these little booklets that, I don't know, people like physical things sometimes, I guess. So there's all different, let me just sort of, there's an R booklet, there's a deep learning booklet, GLM, etc. And then that's my contact information, I guess. And then I want to point you to the last slide on here. I didn't really go into a lot of details about deep water, because that will maybe be for a future meetup. If you're an R person who uses Spark and want to use H2O, there's a package called RSparkling. It's another one that I worked on, which is why you're learning about it. And then this is my favorite new thing that is just got moved over into the public code base, is automatic machine learning, or AutoML. So this is something that I'm working on right now. Essentially everything that we've done, we have a function called h2o.automl, and it will like do all of that for you. And if you really don't want to be bothered with any sort of grid searches or anything even like that, then you should check this out. It's pretty, it's not really released yet, but stay tuned, I guess. And everything can be done automatically. I mean, it's not like, you know, you still have to sort of interpret the models and stuff like that at the end, but it's basically, I would say, a high-level wrapper on top of all the other stuff like grid search and stacked ensembles and whatever, that will do all of that without you having to type in anything. So I'm pretty excited about that. And if you want to try it out, send me an email, and I'll point you to a notebook that you can try it out. I should probably have that link on here, but maybe just send me an email. Okay. So I'm going to stop now, I guess, and we'll have time for some questions, I think, for like 15 minutes or something. So, so yeah, thank you for listening. Yeah.
Could you talk about interpretability a little bit?
Yeah, so there's an algorithm that came out, I don't know, maybe 2 years ago or 1 year ago, that's called LIME. And it stands, I think it stands for locally interpretable. Let me just Google it, but it's essentially a method that will, LIME, machine learning, that will tell you, so explaining the predictions of any machine learning classifier. So essentially what people, oh, and if you stay for like another minute after this, I'll show you what the most important predictors of our thing is. I just remembered that we forgot to do that. So basically, you can get feature importance from like a model, but that's at like a model level, and that's generally useful about understanding your model. But what people really want to know is, like, for this particular prediction that I made, what were the things that influenced it? So when you have regular feature importance, it's like, in general, like, these are the highest, you know, whatever. So this is a way to like quantify the influence of each of the features in your actual prediction itself. And so that's essentially what LIME does. And so we actually have our own flavor of it. It's called K-Lime. I don't know, like, we kind of just, unfortunately, we didn't get like a water analogy in there. It should be called like lime juice or something. I don't know. But so that is, I don't know if that's actually been merged into master yet or if it's on its own branch. But essentially what you'll get back is that. You'll get like a numeric representation of how much did each feature influence the predictor. So this is used like when, for example, you're never allowed in any sort of like lending or like banking type of stuff to include any variables that correlate with race. And so if you train a model, you can see like whether or not that's actually influencing, and it probably usually does. So, well, one way to not do that is just to not include that or like anything that's obvious. But but yeah, this is like in high demand because this concept hasn't really been formalized until recently, and so people come up with like a lot of weird ways to do this, but this is actually like a real like verifiable method that's written by professors at University of Washington. It's like a legit thing. So we have implemented this with like a little bit of a tweak on it, and that will be out soon, I think, in our next release. And then we have a whole bunch of other stuff that we're working on in terms of visualization that will be also connected with that. So that's all sort of ongoing stuff that will be coming out shortly. Yeah.
So, running over your laptop versus like running on the AWS.
Yeah.
What type of examples do you rather go with? Is it the scalability or is it the?
I mean, it's a couple things. It's like scalability is usually why people go over to that, or if they just want things to run and they don't want to like have it be running on their laptop while they're trying to do other work, or like if they're going places. I actually think if you close your lid on a MacBook and H2O is running, I think it starts running again when you open it up, if I remember correctly. So you can actually do that, but yeah, it's more just like convenience of not having to have that on your laptop. And if you're running on all your cores, like it's taking up probably a lot of like CPU. The RAM is maybe not that much, but like these are designed to be CPU heavy and take maximal use of the CPUs. So so yeah, and then if you're like running a business, then maybe that's a good place to do it as well. And yeah, it's pretty cheap to do the instances on Amazon. If you want to start doing GPU stuff, which I didn't get into, that's where it starts to be a little expensive. So I don't know what the trade-off is in terms of buying a GPU machine versus Amazon. I think it's like, I think somebody the other day at H2O was comparing like, it was like a year of running that machine is equivalent to, or wait, after using Amazon GPU, like one of the good GPU instances for a year, you could have just bought a machine. So something like that. So do the calculation before you, if you think you're like gonna invest in GPUs and maybe you want to buy a machine, but again, always good to just try it out first on Amazon and then transfer. Yeah. That was a great question. I'm surprised it took this long for somebody to ask, actually. So we have like a couple different strategies, but so the first one is enterprise support. So like a lot of our customers are just like big companies that need somebody to talk to about their, their infrastructure, and like maybe they have something complicated, or maybe they need like security stuff, or whatever. So just enterprise support, and then for those enterprise support customers, we also do, I guess like feature, I don't know what to call it, like feature prioritization. So they'll say like, I really want you to add like the Tweety distribution to your GBM. You don't have it yet. And we'll say, okay, well, there's all these people asking us for things to do. So like, essentially we prioritize what we're going to do next based on what our customers want. And typically it's basically in line with what everyone wants anyway. So for things like that example that I gave you, the Tweety distribution in the GBM, that was an insurance company, because Tweety distributions are common in insurance data. So maybe that would have taken longer for some random open source user to ask us for that. But yeah, feature prioritization. And then we have kind of like longer term engagements with companies where we're kind of building stuff with them. And they want to build like something on top of H2O, and we kind of help them with the integration. But essentially, like all of the stuff where it's like companies asking for a feature, that goes into the open source. So that there's not like two versions of H2O, or like there's not an enterprise H2O. It's just one version, and people actually are thinking a lot differently about that now. Like people like the open source aspect. I mean, I think it's obvious why like it's so much better than closed source, but I'm, like from Berkeley, and like I think this way, and like normal people don't maybe think this way. I don't know, but yeah. So those are some of the ways that we make money. Yeah.
People use it for the rest of the day, like settling them.
Oh yeah.
So they try to find out the cars and all the parking lot.
Yeah.
I don't know how to do it.
So yeah, so all of the image type data stuff would usually works best with deep learning. So there's something there's a type of deep learning called, or I guess a type of network. So deep learning, it's all like neural networks, and there's different types of networks with different architectures. So the one that's called convolutional neural network, or CNN, is the one where that's most used for like image classification and stuff like that. So for that, you would want to use Deepwater, and one of the three like backends that we have for that, TensorFlow or Caffe or MXNet. But you can, the reason that we made an interface for those tools is because independently they're like a little bit complicated to use. So there's actually a function called Deepwater in H2O, and you just tell it which of the ones that you want it to use. Do you want to use GPUs? Which backends? Like what is, what type of network? Like, and then you can do it all from the same function. So if you want to try the same network on Caffe or TensorFlow, and you're not sure which one to do, you can from H2O just try them both with the same function, and it makes it easy to, rather than setting up a whole thing and sort of, devoting your time or investing your time into one thing, you can just easily switch between the two. Because all three of the libraries that we've added to Deepwater are very good, but sometimes like they're good at one thing and the other one's good at something else. So, so then you have to like switch tools all the time. And then the other thing is that you get all of the standardized metrics that we have, and like it works with Flow. I don't know if I have a Deepwater version installed right now. I don't. But if I did, there would be a drop down that says Deepwater here. So the Deepwater stuff is pretty new. So it's like, it's probably, I think maybe even by next week, it should be kind of like more prominent on our website and like sort of pointing people to use it. Right now it's there, but like we haven't like really officially pushed it out yet. So
sorry for how you get, but
yeah.
I've seen people like flipping out the car, for instance.
Oh yeah.
That's how they train the model. Is that how?
So I mean, there's more like standard computer vision libraries that do sort of, you would have to have a model if you're trying to like recognize a car in a picture. You would have to have a model that's trained on pictures that have cars and not cars and stuff like that. So, so that's more of an issue of how do you get the training data for that. And but there's actually like lots of models that you can just download that are pre-trained, like with TensorFlow, that will do generic object detection. So they've trained on like Google images, basically like the whole thing. And it makes it, so they have models, so you don't actually need the training data. You kind of just use these ones that already exist. Caffe is another one that would have stuff like that. MXNet, I don't know if they have like a pool of models that you can choose from yet, but that could be another option.
Is the grid search also integrated with the TensorFlow backend in terms of tuning?
Yeah,
architecture?
yeah. So everything is like a first-class like model in H2O. So you can do all of that easily. And actually, one of the cool things that I'm really excited about is doing ensembles with TensorFlow and XGBoost and H2O like all together. It's like insane. And I've been like waiting for this to happen for years, and it's like we're finally there where we can do that. Yeah. Okay. So I clicked. So we trained all our models. They're in the H2O cluster, and I clicked on this thing, Get Models, and this will show our models below. So let's see. Just click on the regular. So all of our models have variable importance. So it doesn't matter which one. So this is just what one of our random forests thinks is important. So what I said was that you might be surprised. So the state that the person lives in is actually the highest predicting thing, which is kind of like not that useful, but it's interesting because, you know, I don't know if that means their data set was like kind of messed up where they had like weird data or something like that, but yeah, that happened to be the highest predictor. I mean, and that's probably correlated with a lot of these other things. So if you think about maybe like a lower income state with like more, I don't know, so not California, I guess, like or not the Bay Area. You know, there's just all these other things that are probably correlated with socioeconomic status. I actually don't know what this one means. Revol util. I don't know if it, I mean, utilities or something. I don't know if one's good. Okay, that makes sense. So, DTI, I should probably have like a, what is it? Debt to income ratio. Okay, that makes a lot of sense. So loan amount, annual income. So home ownership doesn't seem to matter that much. Yeah, so, which is good because like no one can afford a home here anyway, so it doesn't matter. So yeah, that was, I mean, each of the models will have their own version on this. So if we looked at, I mean, it's probably pretty similar. But if we looked at, I guess we trained all random forests, so it's probably going to be approximately the same thing. So it will give you sort of like, I don't know what the visualization piece of that will be yet, because that's going to be part of it. But in terms of just data that you get back, you'll get something that actually looks like this, where it's like, this would just relate to like a single prediction. So it would say like address state is the most and then whatever, and it would break it down the same way that you do at the model level, but this is, but they'll all change depending on like, for example, the person that's getting the loan, like certain things might affect that person, other things might affect a different person differently or something. So, so yeah, it would be either like a data frame that you get back, or you can plot it like that as well.
The question is, if you guys use the ensemble,
Yeah.
as a predictor, is there a correlation with what sort of ensemble versus this particular?
So with the ensemble, like you see which of the models are like, what you get back is you see each of the models and the performance in there, and then you see the ensemble model performance, and you can kind of get a sense of like which models, like if you start using the ensemble thing a lot, you'll start to see like patterns where it's like basically GBMs always like win everything, and then deep learning, and then you know, GLMs are always like the worst. And you know, it's all like data dependent, so I'm not saying like GBMs are always going to win like everything, but most of the time, like in my experience, they're always doing the best, and then the ensemble will do a little bit better than that.
For this particular
The correlation of what?
That address and state.
I don't think I understand your
So it
question.
says that we have 5 specific algorithms.
Yeah,
Right?
yeah.
But we have a slew of them.
Mm-hmm. Yeah.
Has that data set been trained other models with,
Oh,
so that
yeah.
you know the defining characteristic is the state.
Yeah. So if I were to, if you go back to this and run it yourself, you can run the GBMs and the deep learning and the GLMs, and you can look at, I mean, in theory, they should kind of all agree on what's important, but they don't. They have different. Each algorithm has its own way of deciding what's important. So it might rank things differently, and there might be different differences. So there's not like really a true, like a truth of like what is correct. It's just they're all approximating in their own way. So so one thing you could do would be like average them together if you're interested in sort of a more generic look at the variable importance. You could say like, well, I'm not going to listen to this one. That's not going to be the truth. I'm just going to kind of look at them all together and see, if every single one says address state is important, then it's probably really important. Yeah. Right. Yeah. So it depends on the algorithm. So like deep learning would be good for nonlinear stuff, and I guess the tree-based methods would be good as well. But like that's deep learning. What it's sort of designed to do is to take a linear model and like expand that into like a crazy version where there's all this nonlinear stuff going on. So yeah, a deep neural net is essentially a bunch of like little linear things put together in like a massive network.
Sort of like a linear aspect type?
I don't know if I would call it that, but they're all fitting. They're all like what you get with a model is a function that can like produce sort of like I guess like with a linear model you actually literally get a line that would go through. The random forest is very different, or like the tree-based methods are very different. Rather than a line to split up the space into like let's say 2 pieces, you actually get like a bunch of squares where it's like, let's say you're like if you color the squares like green and red, like green is default and red is not default or something on this lone problem, you would get like weird patches of things where it's like, if you as a person fall into like this area in the high dimensional space of all these features, then this patch is like, might be like a little red patch, and then there's a little red patch over here and green over here. There's actually good visualization. I think maybe it's on the scikit-learn. I know we actually have our own visualization of this, but I don't know how to find it easily, so I'm going to do scikit-learn. Decision boundary. So this is a good image. This shows a bunch of different algorithms and how they are able to create these boundaries. So when you think about what a classifier is doing, it's like defining a boundary in space between this kind of stuff and that kind of stuff. And then the algorithms have essentially different abilities to divide up that space. So this one, k nearest neighbors, is interesting because it kind of just like goes, it's determined sort of by the data itself, whereas decision tree, anything with a tree is dividing it up into pieces and chopping it up with lines like that. So this is regular decision trees, just squares, and then random forest would be like more finely chopped squares. A neural net looks like this. So there's all like, so the ability to chop up the space in any particular way is defined by the algorithm itself. And so if you had, for example, data that looked like this, where there was like a cluster of stuff in the middle and then other stuff on the outside, then a linear model would be like a really bad choice because you can't put a line through that. You need like something that can go around that little circle of data. And so that's kind of what it's showing here. Yeah, so I think we'll, yeah, one more question.
So, I think you said there were 15 characteristics of each row, and there wasn't 15
Oh, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I think there might have just been, I think there was 15, but then one of them was the response column and one of them was interest rate, so we're left with 13. Yeah. All right, so I guess, oh yeah, one more question.
So, I've noticed that on Kaggle, the two main things needed are ensembles and synthetic features.
Yeah.
So, is there a way to generate features, maybe using genetic programming, something like that?
There's not like a general purpose way to do that, but there's techniques that people have that are sort of well defined, and that's something that we are working on for AutoML, but we don't have that like as part of our first release. We're just concentrating on the algorithm itself, and then we're going to expand possibly to include other things that would auto-generate features. But that's kind of like a black art. So there's if you're a Kagler, you have like all these weird techniques, and maybe you have some domain knowledge that you use to create the features. So what we're trying to do is like systematize. Like there's I think 4 or 5 top Kaglers, including I think the guy who's ranked #1 works for H2O. There's this guy. His name's Casanova. Oh, he's currently ranked 2, so that's too bad. Not 1, no. So he's one of the best Kaglers in the world, and he's starting to work at H2O in June. And so basically, our Kaglers are the people that are working on this stuff. It's like they have their own like techniques, and now we're taking their brains and trying to put that into a system that can be automatic. All right, so I think we have to get out of here. So I will shut this down and stop this recording.